Hello everyone, welcome back to our malware analysis course. In this section, we are going to explore the course static malware analysis by dissecting the PExecutable file format used in Windows. This knowledge is essential for reverse engineers and threat analysts to identify the malware behavior without even running the binary. So, first thing first. What is static malware analysis? Static malware analysis involves examining a file contents and structure without executing it. The goal is to gather insights about the malware capabilities, intents, and possible indicators of compromise. Some of the techniques used in the process are extracting readable strings, disassembling the code, parsing the PE headers, examining embedding resources, and analyzing the import-export tables. Understanding of PExecutable file is inevitable for static malware analysis. What is a PExecutable file? PExecutable file stands for Portable Executable, the standard format for the executables and libraries in Windows. That includes .exe, .ell, .sys, .scr files, etc. A PE file is like a layered cake with multiple sections stacked logically. The main components include DOS header, PE header, optional header, sections table, the actual sections including text, data, resource section. The structure of PExecutable file may look a bit complex, and it may seem a bit theoretical also. But trust me, understanding the structure and various things which you should notice, the anomalies which are present there, is very important as a malware analyst. I will request you to make some notes and bear with me for next 5 to 10 minutes. And trust me, the results will be very fruitful. You will be able to gain insights about various malicious artifacts of the suspicious file without even executing them. Every PE file starts with a DOS header. This is a leftover from MS-DOS days, but it is still essential. It always starts from first 2 bytes 4D5A, which translates to MZ. It is very interesting to note the MZ in a PE header stands for Mark Zimowski, a Microsoft engineer who worked on early DOS. The signature tells the loader that this is a valid executable. Within the DOS header, there is a crucial field at the last which is known as ELFA new, which is the offset to the actual PE header. This is how Windows locate the next step in the parsing process. After PE header comes the DOS stub. This is a tiny 16-bit program. If you try to run the executable on a DOS system, this stub prints a message like, "This program cannot run on DOS mode." While not essential for malware, it ensures backend compatibility of Windows executable files. If we see this and load any malware sample, now for demonstration purpose, I have loaded the PE file of calculator.exe, which is the Windows calculator, to show you how this DOS header looks like. You can see it starts from 4D5A. Here also you can see MZ. And you can also locate the DOS stub here, which shows that this program is running on a DOS mode. Now let us discuss about various anomalies which you can notice in the DOS header, which can help your malware analysis process. First is to check the magic number, which should be MZ. If it is missing or altered, the file might be corrupted or packed. Second is the P offset, the last bit which I just told you, which points to the location of the entry headers. If it is pointing to an unusual location, it may indicate that this is a packed file. Default message which appears that this program cannot run in DOS mode. If this message is altered, it may be indicative of a malware. I will show you all these anomalies in live malware samples and how they are altered. But have some patience and wait for the actual static lab part. Till then, please note these points, and I promise you that I will show all these things in live malware samples. The next is PEheader, which contains file signature, image file header, and image optional header. You can see on the right side the structure of PEheader. The first section of the PEheader contains important information like machine architecture, number of sections present in the PE file, the time date stamp indicated when the file was created and modified. This field is very important to know when was the file actually compiled. Any modifications or alterations in this can give us significant indications to its suspicious nature. Then other informations like size of optional header and other characteristics. The anomalies which to notice in PEheader are time date stamp. Common malware time date stamps like for 1970 or 2009 or 1992 even are used by generic packers. So if these timestamps are used, then there may be an indication that these suspicious samples are altered. The entry point. The entry point of the malware should be inside the text section. We will discuss about various sections in the sections part. If it points to any other section or like data part or resource section, it could indicate that the malware is packed. Subsystem. Normal Windows executables have a Windows GUI or console. If it is unknown or something other, it may be suspicious. So keep a note to check the entry point, mismatch in the image size and the sections. For example, a PE file which has an entry not in the text section might be a packed or a Trojan hiding inside the code. We will see this in our example of when we compare a packed and an unpacked malware file. Next comes the PE optional header. Despite the name, optional header is not really optional. It is mandatory for executables. It contains information like the address of the entry point, image base, size of the image, subsystem used, data directions, which includes the import address table and the export address tables. You can see on the right side of the screen the data structure of image optional header, which includes a very important information as mentioned. It also includes the checksum, which also indicates that the malware has been modified or not. Next we encounter the section headers for each segment of the file. Each header describes the name of the section, the virtual size, raw size, virtual address, raw data pointer, and characteristics. There are mainly 7 sections which are available. First is the text section. The text sections contains the executable code. It is actually the entry point from where the code execution begins. That is why it is given read, write and executable permissions. Next is the data sections, which is used to store initialized variables and strings. Data section also has read and write sections. Next is our data sections, which it holds import address tables, addresses to Windows APIs and DLLs used. It is only a read-only section. This section gives us information about the various functionalities of the suspicious file. Next is the resource section, which resources the executable file icons and images which we see in the executable file. This is also a read-only section. Next is the debug section, which includes the debug information. There are other sections like eData sections, which includes the list of exported functions of the DLL, and iData sections, which includes the list of imported functions from DLLs. There are some other sections also which may be present in the PEexecutable file. It is worth mentioning to note that when a malware is packed, there may be some other sections also apart from these mentioned sections. If there is any unusual section which indicates the suspicious nature of the file. Now, various anomalies to see in text section. If the size of the text section is very tiny, but data section is large, this suggests that there is some obfuscation of code. Then, entropy analysis. Entropy is the randomness of the code in the PEexecutable file. Generally, when the malwares are packed, the randomness and the entropy of the suspicious file get increased. So higher the entropy indicates that the malware is packed or it has some encrypted codes. I showed you about the various permissions which were there in the sections of the PEexecutable file. So the text section, which contains the executable code, should have proper permissions. Again, if there are any unusual sections like .data1, .upx, .xyz, then it shows that the malware authors have renamed these sections to avoid detection. We will cover all these things when we analyze our malwares in the static lab. The R data section typically holds read-only data, including constants, strings, and most importantly, the import address table. First, check the IIT. If it is missing or it is unusually small, it could mean that the malware is dynamically resolving the API functions at runtime. The most common technique used by packed or obfuscated samples. Instead of having functions like create file A or write file listed statically, the binary uses functions like load library and got address to resolve APIs manually. That's your first red flag. Manually resolved imports using load library A or load library W. Get process address is another API call to look for. Why do attackers do this? Because it helps to evade detection. Antivirus engines scanning the IIT might not find any suspicious API calls if they are resolved dynamically. The R data sections often contains a string. If you see long random looking strings, they might be base64 encoded payloads, XOR of cascaded commands, or even encrypted configuration data. Look for hard-coded IPs, domains, registry paths, or command line payloads like PowerShell or CMD. These are usually dead giveaway or of a backdoor or Trojan. Catching these anomalies early can reveal packed malware, encrypted payloads, and stealthy Trojans trying to fly under the radar. The data section typically stores initialized global and static variables. But when abused by the malware, it can hide payloads, encrypted keys, and even shellcode. Then what to check? First of all, check the section size. Check the size of data section. If it is abnormally large, that's suspicious. Malware authors often embed entire payloads or large encrypted blobs here. Then, second, look at the permissions as well. If the data section is marked as read write execute, that's a major red flag. Legitimate programs rarely do this. If ever, need to execute code from a writable sections. As I told you that RWX permissions are generally given to text section which contains the actual code of the PExecutable. If the data section has RWX permissions, this suggests that the section may contain self-modifying code, meaning the malware writes and executes the code dynamically. Encrypted shell code. You might find base 64 strings, high entropy blobs, or unusual byte pattern here. This could be encrypted shell code that the malware decrypts at runtime and executes from the memory. Because it is stored in a writable section, the ransomware can modify or destroy the key later, making decryption nearly impossible without the attacker's help. These signs often point to advanced malware behavior, including runtime decryption, fileless execution, or anti-analysis techniques. Normally, resource section contains legitimate sources like icons, dialog versions info, or images used by the applications. You may see various icons like the close symbol or the dialog symbol which appears in a PExecutable are stored in this section. But in malware, this section is often repurposed to hide payloads. Check for the embedded executables in the resource sections of the PE headers, like another MZ signature. This may indicate that the entire executable is hidden inside the resource section. Look for base 64 encoded strings, encrypted blocks, or large sections of the binary junk. These often turn out to be obfuscated payloads waiting to be extracted. Packed malware often packs secondary stages of payload inside the resource section to evade detection. This is especially common in droppers and downloaders. Unusual size of resource sections, which is typical for bin-in programs. If it is unusually large, that could suggest that it is hiding something malicious. Even if it contains permissions like read write execute, then also it may be flagged as suspicious. So when analyzing the resource section, keep an eye for MZ headers indicating embedded executables, base 64 or encrypted blocks, large size, and resource loading API calls in the assembly. These signs often hide to payload hiding, packing, and in-memory execution techniques. In this section, we are breaking down something every malware analyst must understand: the Windows API. It is used by all the Windows programs, good or bad. In fact, Windows API is what makes the Windows softwares work well. But it's also the exact toolset malware authors use to exploit and manipulate the system. So how does this same system of functions become both the builder and the breaker? Let's find out. The Windows Application Programming Interface is a collection of pre-built Windows functions provided by the Windows operating system. These are like Lego blocks that the developers used to build software that interacts with the system. Let me give you an example. Want to open a file? Then use the Windows API function create file A. Want to draw a window on the screen? Use the API function create window X. Similarly, to connect to the network, there are separate Windows API functions like WinHTTP send request or internet connect. Similar options are available for almost all the functions on the Windows program. These all are Windows API functions. Without them, developers would have to write complex code from the scratch to interact with the system memory, hardware, networking stacks, which would be incredibly inefficient. Genuine softwares use this API to save and load files, handle user input, connect to the internet for updates or cloud sync, display geo elements, manage the memory and resources, interact with the hardwares like printers and webcams. So in short, legitimate Windows software absolutely depends on these API functions to work well. So how they are misused? Malicious softwares use the same APIs but with different intent. The Windows API is so powerful and has such great power that it can easily be used by the malware authors for malicious intentions. Malicious malware authors exploit these very same functions to carry out their goals. For example, they use virtual alloc X, write process memory, or create remote thread for process injections into genuine applications like explorer.exe or svchost.exe. They use registry API calls to maintain persistence and create entries in autorun registry keys so that the malware launches every time the Windows boots. For evasion also, they use API calls like virtual protect to unhook security APIs and evade detection. There are various API used for command and control and encryption as well. So the malware is simply reusing the legitimate tools of the OS. What matters is how these tools are used. As malware analysts, this pushed us in an interesting position. You can't just flag the file just because it uses create file or registry API calls, because every app does that. But if you see virtual alloc followed by a write process memory and create remote thread, this is highly suspicious. Calls to load library and get process address to resolve the function at runtime, that might be an attempt to avoid static detections. Calls to win HTTP send request paired with encryption routines, you're likely looking at data exfiltrations. So here the pattern and the context matters. And that's why understanding Windows API usage is one of the most important skills in static malware analysis. Windows API is not an evil, it is essential. Every Windows application relies on it to function properly. But if malware authors abuse its powers to perform malicious actions, often trying to blend in with the legitimate software, that is why analysts, we don't just look for the APIs are used, we look how, when and why they are used. In the static malware analysis sections, we will see various APIs imported by the malware, and in dynamic malware analysis section, we will see how they are called, how they are used, and what are the applications which they are calling. Now, let me introduce to an incredibly useful utility that can supercharge your malware analysis process. malapi.io is a powerful online resource designed specifically for cybersecurity professionals, research engineers, and malware analysts. It is created by professional security researchers. This platform maps Windows API functions to common malicious behaviors, helping you quickly identify suspicious activity in the binary. When analyzing the malware, understanding API functions are being called and why is crucial. Mal API categorizes these API functions based on common tactics used in cyber attacks like enumeration, injection, evasion, spying, internet, anti-debugging, ransomware, helper, etc. So, these are various tiles which are available. Whenever you click a tile, some description about this Windows API function opens up, such as function name, which is create process A, the description of the function that it is used to create a process. This function is used by malware in several process injection attacks, such as process hallowing. It also mentions the DLL which it uses, the associated attacks, and the official Microsoft documentation for the same. If you click this, you will be able to access the official documentation which is available for this function. Here you can study these functions in detail and see what are the inputs which are being taken. For now, let's concentrate on only the Windows API functions, because this will be covered when we will cover our reverse engineering process. So, what makes it super convenient? Whenever we are analyzing statically our malware samples, we can match the suspicious API usage with category like key logging, evasion, or persistence. We can also use malapi.io to enrich detection logic by identifying the key behavioral APIs. Mal API acts like a cheat sheet for malicious behavior, giving you instant insights about how Windows API functions are called, how they are abused by the malwares. It is ongoing and ever growing resource. New APIs and their techniques are regularly added. If you are diving into malware analysis process or building some detection tool, this is a must-have tool in your arsenal. This refers to any data appended to the end of the PE file, beyond the last defined sections in the PE headers. Sometimes this data is harmless, like data signature or installer metadata. But in many cases, malware authors use it as a secret storage for payloads. Look out for the size here. If the total size of the predefined sections is smaller than the overall file size, it means that there is extra data at the end, and that's your overlay. Using entropy analysis tools, look for overlay region that has very high entropy. That means it contains packed or encrypted shellcode. Manifest files hidden in the overlay. Malware may hide or tamper with the embedded application's manifest files, sometimes storing it in the overlay or resource sections. Watch out for user access related settings in the overlay. Basically, there are three types of settings, which is as invoker means the malware runs with the current user privilege. Require administrator. In this, malware prompts for the privilege acceleration where it needs administrator privilege to execute. Third is highest available. That means that it runs with the highest privileges available to the current logged in user. Malware often abuses require administrator or highest available to bypass the UAC and run with elevated privileges, allowing them to make system level changes like in the registry or system32 silently without being noticed. These settings are usually declared in the manifest, but if it is hidden in the overlay, standard tools might miss them unless you inspect them manually. Overlays are common hiding spots for malware to sneak in additional stages, config files, or elevation tricks. Malware authors are becoming increasingly sophisticated, and one of the ways they try to bypass detection systems is by using legitimate signed PE files. These signed files appear trustworthy to the users and security tools, allowing the malware to go undetected for longer periods. By signing their malicious codes with valid certificates, attackers make their malware look like a legitimate application. But here is the key. While these files might look safe on the surface, there are still ways to identify them as threats. In this video, we will look over the critical signs to look out when analyzing the data signatures in PE files. First, let's talk about unsigned system-like PE files. Legitimate Windows system files like svchost.exe are almost always signed by trusted certificate authorities. If you come across a system file like that's unsigned, that's a red flag. Because the system files are essential to Windows and their signature are crucial for confirming their legitimacy. If you spot an unsigned version of a system like PE file, it could be very well a malware. Next, let's look for fake or expired signatures. Malware can use stolen or revoked signatures to sign their files, making them appear legitimate at the first glance. This can be particularly tricky because many malware samples use certificates that were once trusted but now either they are expired or they are revoked. So it's vital to check the certificate's validity period and revocation status. Tools like SignCheck or PFile can help you quickly assess the file signature and certificate status. Finally, watch out for self-signed executables. These executables signed with certificate that the author has generated themselves. While software developers rarely use self-signed certificates, they are often go-to for malware authors. Self-signed certificates provide no external validation of trustworthiness, and when seen in executables, it should raise suspicions. Always verify whether the certificate has a trusted issuer, especially for executables files that don't match the expected publisher names. For example, let's take an example of Stuxnet, one of the most infamous malware examples of malware using legitimate signatures. Stuxnet was signed with the stolen data certificates from two legitimate companies, Realtek and Jmicron. These certificates allowed Stuxnet to bypass many early detection mechanisms by appearing trustworthy. This is a perfect example why analyzing data signatures is so crucial in malware analysis. Attackers can make their files look completely legitimate, but a closer look at the certificate status can reveal the truth. So finally, to wrap it up, check the certificate's authenticity, verify the signature's validity, inspect for self-signing certificates. In conclusion, while legitimate signed PE files can appear trustworthy, often used by malware families to avoid detection. By being vigilant and knowing what to look for, unsigned system-like files, fake or expired signatures, or self-signed executables, you can significantly improve your ability to identify malicious files. Remember, data signature analysis is just of the many techniques in your malware analysis toolkit. But when combined with other methods it can be incredibly powerful in identifying the threats. Hello everyone, welcome to Malware Analysis course by Zero Trust Labs. This GitHub repository provides real-world malware samples for hands-on training in malware analysis, reverse engineering, and incident response trainings. These files are live malware samples. If you open them or run them on normal computer, they can infect your system, steal data, or communicate with real-world command and control servers. They can bypass antivirus software and spread across the networks if not properly contained. Opening them accidentally in a file previewer or even a text editor may trigger malicious behavior. That is why you must use these files only in safe environment. To get this repo, click on this green code button from where you can download the zip of the malware repository. As you can see, the malware repository has been downloaded. Set up a secure virtual machine using Flare or Remnix as shown in the video before. Disable internet access or use host-only networking. Never connect your VM to your home or office network. Follow these precautions to have a safe hands-on learning experience. The link of the repo will also be mentioned in the description. Stay safe and happy hunting. Now, the next task is to move your malware samples to your Flare VM. For this, we will use the Share Directory feature of Windows VirtualBox. Here, as I have shown you, that I have downloaded my malware course repository in a zipped form in a shared folder. I have made this shared folder on the desktop. Now, I will go to my VirtualBox. In the VirtualBox, in the VM setting, I will click on Shared Folder feature. From here, you can mount this shared folder to this virtual machine. I will go to desktop and select this sharing folder. Click OK. Okay. Now, in the virtual machine section, if you will open the Explorer and go to the network section, here you will see your shared folder. This is our malware course repository which we want to work upon. We will copy this to our Flare VM. Copying this folder to the Flare VM, we will now remove the shared folder because some of the malwares have capability to compromise this shared folder also. So taking full precautions, we will now then remove the shared folder from our VirtualBox settings. Click OK. When you go back, you will see that the shared folder is not available now. Now unzip this shared folder here. Here you can see all the samples which we are going to use for our code. Welcome to Trial Strike. This is your first mission in our malware analysis battlefield. And today we must face the real threat, CryptoLocker ransomware, the digital equivalent of smash and grab heist. What is Trial Strike? Trial Strike is the first exercise in our series where we don't just learn about malware, we see it in action, we detonate it, we watch it destroy, and later we will break it apart piece by piece to understand how it works. CryptoLocker hit the world in 2023 like a digital nuke. It arrives silently through a fake invoice or zip attachment. The moment it is executed, it begins encrypting files rapidly and relentlessly. Then it leaves a chilling message. Your files are encrypted, pay up or lose them forever. No mercy, no backup, just chaos. The sample will be detonated in high security virtual machine as we have set up. Internet is disconnected, network is isolated, and before doing anything, we will make a snapshot of our virtual machine. Remember, I will say it again, do not try this on your personal system. This is life dangerous code. In the first step, we will take a snapshot of our virtual machine. For this, go to this machine in the top toolbar and click on the option Take a Snapshot. Here, we will name our snapshot pre-detonation. This will save the state of virtual machine as it is now. Just wait for the snapshot to complete. So now we have successfully made our snapshot. So to execute our first malware sample, we will go to our samples repository. Here you will see the first section named Trial Strike. Here there is a malware sample named ransomware.cryptolocker.zip. Extract this using the password infected. Here you can see there is a live malware executable file. Please do not forget to make a snapshot for pre-detonation stage. Now we are all set to detonate our first malware. After double checking everything, all the network settings and lab setup, I will go and execute this malware and see what happens. Let's go. Now observe the changes the ransomware makes on the virtual machine. You can see now we cannot access our normal Windows Explorer. There is some sort of a screensaver which is visible to us, which says that files have been encrypted, etc. etc. This is why incident response matters. This is why backups, isolation, and awareness are very critical while analyzing malwares. Had we not taken snapshots or proper backup solutions, we won't be able to recover our virtual machine. But thank God, we have done that. In the next lessons, we will learn how these malware works and what are the effects of these malwares on our base system. This is Trial Strike, and this is just the beginning. Join me in the next video to see static malware analysis and see what are the behaviors of malwares and how they function. Welcome back, analyst. In the last exercise, you witnessed CryptoLocker in action, the raw chaos the ransomware can cause. Now it's time to understand the lab and how to safely prepare and load the malware samples from the lab environment. We have already downloaded the malware codes zip from our GitHub repository. We have also shared them inside the virtual machine using sharing folder feature. We have removed the sharing folder and unzipped this malware codes zip on our desktop. Here you can see the samples folder, which contains all the samples which we will require for our malware codes. We have already used the first sample for our trial strike section. Now for our second section, we will use the second sample. The structure of the lab is like that. Here you will have a zip of a malware, password which is used to zip this folder, and SHA-256 of the malware sample. Extract this zip using password infected. Here inside that you will see the malware sample in a pre-decided nomenclature. Here I have appended something after the malware file so that it doesn't execute accidentally. To load this malware, you have to just rename it and remove the extension which I have appended after it. Once you remove the malware, now it will prompt for a UAC, click yes, and now it is a live malware which can be used for our analysis purpose. Please remember to take a pre-detonation snapshot before executing anything so that we can recover our VM once it. Please do not forget to take a snapshot of the VM before detonating or running the malwares so that we are able to roll back to those snapshots once the VM is infected. And we will do this again and again during our malware exercise. You have seen how malware attacks. You have also seen its impact, but now it's time to learn how it hides. Today's lesson is malware packing, the digital art of deception. Malware authors rarely deliver their payloads in raw, unprotected form. Instead, they pack them, wrapping the malware inside a layer of encryption or compression. It's like sending a bomb inside a birthday gift box. Your antivirus, it sees the gift wrap, but not what's inside. Why do attackers use packers? First reason is to evade antivirus. Most AVs scan the known binary signatures. Packers break those signatures. Second is obfuscated code. It becomes harder for the analyst to reverse the packed malwares. Third is delay analysis. Before you can understand what it does, you must first unpack it. So there is a huge time loss in the analysis process. Some of the malware even uses custom packers that mutate the pre-built packing, making each sample look unique. Some of the common packers include UPX, NSPack, ASPax, Themida, etc. If the malware sample seems oddly small or unreadable in the hex editor, chances are it's packed. Now, in this demo, we will analyze side by side the executable file known as Notepad. Notepad is a common utility text editor which is used in Windows. Here we will see the analysis of packed notepad versus the unpacked notepad. For this, go to your malware samples lab, open samples, and in static malware analysis, open the first section which is packed versus unpacked malwares. Copy this to your desktop and unzip it. Here you can see that we have two malware files, or say notepad files. One of them is packed and one of them is unpacked. We will use a utility software known as PeStudio to open both these files and see what are the differences between them. So first of all, we will first rename these and remove the extension from them. One thing which you can very predominantly see that the size of one file is different from the other. One file is considerably very smaller, almost 50% of the other. Now open up PeStudio. You can download PeStudio from internet. It is a very common utility available. Here we will open our first file. To go to text. So I have loaded both my samples in PeStudio side by side. On my left hand side is the unpacked sample of Notepad, and on my right side is the UPX packed sample of Notepad. Now one by one I want you to show what is the difference when any executable file is packed. Here the hard work which we did in understanding the structure of PExecutable file will come in very handy. So the first difference which I want you to notice is the file size. Here the file size is around 197 bytes, but here the file size is significantly very smaller. If you see the entropy also, entropy of the unpacked file is around 6.3, but when it is packed it becomes 7.8. The second change which I want you to notice is the entry point. Remember, entry point is a point where the PExecutables empty headers are stored and the code execution begins. Here you can see in the normal notepad executable file, the entry section is in the text section. which is correct, and it should be normally be like this. But in the packed file, the entry point is not in the text section. We will later see that what is the location and where this entry point is leading to. The third point which I want you to notice is come to sections part. The unpacked file contains sections like text section, R data section, etc. and etc. These are normal data locations. But when you come to the sections of the packed file, you will see significant differences there. When you will see the sections of the packed file, you will see instead of text section there is a UPX0, UPX1 section. And also note about the permissions which these sections have. The text section normally has read, write, execute permission. Data section has only write permissions, which are absolutely correct in the normal file, but in the packed file these are changed. The next point which I want you to notice is come to string section. In the string sections you will see various strings which is the actual text which is contained in the code of the program. But in the packed file you will notice that the strings are considerably lower. This happens because of the packing of the samples. One another thing which you can notice in the optional header is the file checksum. You can see here the file checksum is not as expected and it is different, which shows that there is some kind of manipulation in the file. Another thing is the entry point location. As I told you, for genuine files the entry file location should be in the text section, but here you can see in the packed file it is in the UPX1 section, which shows its malicious nature. So when it comes to packed files, we have noticed that they have a smaller file size, their entry location is different, they have various indicators like in sections where the sections are not as usuals, the permissions in the sections are abnormal. We have also seen the entropy of the packed file is more. Then we have seen that the strings which are there in the packed files are sort of encrypted. We have also seen the import address tables and the checksum. So these are some of the things which we need to notice when we analyze any file for static analysis. Remember, packing is first line of defense for malware, not for protection but for evasion. Recognizing packed binaries is a critical analytical skill. There are various tools like PeStudio, Detected Easy, UPX, etc., which will help you to uncover these things. So we will go further ahead and do one more thing. We have seen this file has been packed using UPS packing. Now we will go and unpack this file. To unpack this file, we will use UPX, which is an inbuilt utility in Flare VM. We will open CMD as administrator and go to this location and then type command UPX D for decode and enter the file name. Now our packed file has also been unpacked and you can see it is of the similar size as of our earlier file. We will again open PeStudio and open our recently unpacked file to see what are the changes are there in the unpacked file. Again open that file notepad2.exe. Wait for PeStudio to analyze it. It will take some time. You can see here that already the file is restored. Our entry point is in text section. All the imports are now visible which were earlier hidden. Our sections are also normal like text section, R data section. All the UPX sections have gone. So this is how you can unpack the files after recognizing that what is the packer which is used to pack the file. This skill will go very handy when we analyze our complex malware samples, ransomwares, and trojans, which are generally packed by the malware authors. Let me introduce you to another powerful resource that deserves a place in every malware analyst, reverse engineers, and red teamers toolkit. FileSec.io. FileSec.io is a comprehensive knowledge-based focused entirely on file format security. Built by cybersecurity researchers, it is designed to help you understand the structure, manipulation techniques, and exploitation methods of various file types. All of these are critical when analyzing malware, investigating phishing attacks, or performing digital attacks. So, there are millions and billions of file extensions which are available, which are commonly used by the operating system. To identify or to categorize which of them is malicious or which can be used in malicious activities is very important. FileSec.io does all for you at one place. Attackers frequently embed malicious payloads in every file format like PDFs, Word documents, Excel spreadsheets, archivers, or even image files. These seemingly harmless files can be weaponized to deliver malwares, exploit vulnerabilities, evade detection systems. So FileSec.io becomes incredibly useful as it helps you to see how these formats are abused and why they are effective in real world attacks. So what does this tool does for you? It has various categorization of files extensions, the attacks which they are used, and the operating system which it supports. For example, if we take an example of .7z, it is used in phishing attacks as a file archiver. It is common for all most probable operating systems like Windows, Mac, and Linux. Similarly, there is .a3x file extension, which is used generally as an executable or a script in Windows. You can also click on this link to read more about it. For example, there is a information available regarding this .a3x file extension which is used by the AutoIT v3 compiled script. This information can be very handy while analyzing our files during malware analysis. So it is also a comprehensive list which contains various kinds of file extensions. It can be very handy in static analysis. When you receive a suspicious file, you can get an idea from here that what this suspicious file does and how it can be harmful. Moreover, there is one other feature. There is a categorization here. You can click on this categorization and you will see all the extensions linked to this category. For example, when I click executable, I can see various details about this. If I click phishing, I can see various file extensions which are used in the phishing attacks. Same can be done for macros also. You can see there are extensions like .asd, .doc, .potm, etc, etc. As I told you, the details about these can also be received by clicking on this link. So, FileSec.io is your go-to reference for analyzing file-based threats. Whether you are a reverse engineer or a malware analyst, document building and studying file-based exploits, this platform gives you a context and clarity that you will need.